Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand tapestry of 20th century physics, where colossal theories like relativity and quantum mechanics redrew the cosmos, there exists a parallel and equally profound narrative, the relentless pursuit of precision. This is a story of measurement, of refining our ability to query nature with ever-increasing acuity. It is within this demanding tradition that Norman Foster Ramsey stands as a titan, a figure whose intellectual contribution, the Separated Oscillatory Fields Method, represents a conceptual leap of such elegance and power that its full recognition by the Nobel Committee in 1989, some 4 decades after its inception, seems almost a historic inevitability. Ramsey's method was a masterful circumvention of a fundamental barrier, a technique that transformed the art of spectroscopy into a science of unprecedented accuracy, thereby laying the very foundation for modern timekeeping, navigation, and ongoing interrogation of the universe's most subtle. The intellectual stage for Ramsey's innovation was set by his own mentor, Isidor Rabi, whose development of the molecular beam magnetic resonance method had itself earned a Nobel Prize in 1944. Rabi's technique was revolutionary, allowing physicists for the first time to measure the magnetic moments of atomic nuclei with remarkable detail. The principle was a beautiful application of quantum mechanics. A beam of atoms would traverse a region containing a static magnetic field and a superimposed oscillating radio frequency field. When the frequency of the oscillator precisely matched the energy difference between 2 quantum states of the atom, a Lama precession, the atoms would flip their state. By detecting this change, one could pinpoint the transition frequency. The sharpness of this resonance peak, and thus the precision of the measurement, was governed by the Heisenberg uncertainty principle. The uncertainty in the measured energy is inversely proportional to the duration of the atom's interaction with the oscillating field. To achieve a narrower, more precise resonance line, one required a longer interaction time. Herein lay the central dilemma. Simply extending the length of the apparatus to increase the interaction time introduced a pernicious practical problem: magnetic field inhomogeneity. Creating a perfectly uniform magnetic field over a large volume is a formidable engineering challenge. Any spatial variations in the field strength across the interaction region would present different atoms with slightly different transition frequencies, effectively blurring or broadening the delicate resonance line and sabotaging the very precision one sought to gain. Physics had seemingly encountered a frustrating ceiling, a trade-off between interaction time and field purity. It was into this impasse that Norman Ramsey, then a young physicist at Harvard, introduced his brilliant and deceptively simple solution in 1949. Instead of grappling with the brute force engineering of a long, uniform field, he reimagined the entire interaction. His Separated Oscillatory Fields Method proposed splitting the single, continuous interaction region into 2 short, distinct regions, separated by a much longer, field-free drift space. The genius of this arrangement lies in its manipulation of quantum phase. As a particle in the atomic beam enters the first oscillatory field, it receives a short, sharp pulse. This pulse places the atom's quantum state into a coherent superposition of its initial and final states. It is a preparatory kick, creating a delicate quantum ambiguity with a well-defined initial phase relationship. The atom then exits this first region and enters the long, empty drift space. During this extended transit, which can be made far longer than any practical single interaction region, the 2 components of the superposition evolve. Their wave functions oscillate at slightly different frequencies, corresponding to their different energy levels. This causes a relative phase to accumulate between them. The amount of accumulated phase is directly proportional to the energy difference and, crucially, to the long transit time between the 2 fields. Upon reaching the second oscillatory field, which is locked in phase with the first, the atom receives another identical kick. The final outcome of the second interaction, whether the atom completes its transition or reverts to its initial state, depends exquisitely on the phase relationship between the atom's evolved superposition and the phase of the second field. The result is a quantum interference phenomenon. When one plots the probability of transition as a function of the oscillator's frequency, the broad resonance peak of the Rabi method is replaced by a much more complex pattern. This pattern consists of a series of sharp interference fringes, now famously known as Ramsey fringes. The central fringe of this pattern is extraordinarily narrow, its width being inversely proportional to the long travel time between the 2 separated fields, a duration denoted t. The final transition probability exhibits a dependence on the cosine of a quantity, that quantity being the difference between the oscillator frequency and the true atomic transition frequency, all multiplied by this long travel time t. By decoupling the determinant of precision, The travel time, from the technically challenging requirement of field uniformity, Ramsey had shattered the previous limitation. The short interaction regions could be engineered for high field quality, while the long drift region, being field-free, was immune to the problem of inhomogeneity. This was an act of profound intellectual judo, using the principles of quantum mechanics to sidestep a stubborn classical constraint. The immediate impact of this discovery was nothing short of transformative, most notably in the domain of metrology. Ramsey's method was the enabling technology for the atomic clock. Physicists quickly realized the hyperfine transition between two specific ground states of the cesium-133 atom provided an exceptionally stable and reproducible frequency. Applying the separated oscillatory fields method to a beam of cesium atoms allowed for an interrogation of this transition with an accuracy previously unimaginable. The resulting resonance was so sharp and reliable that in 1967, the international scientific community took the extraordinary step of redefining the fundamental unit of time itself. The second was no longer tied to the fickle astronomical motions of the Earth, but was instead defined as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Every globally synchronized clock, every global positioning system satellite calculating its position with nanosecond timing, owes its existence to the precision unlocked by Ramsey's interferometric technique. Concurrently, Ramsey himself extended these principles to invent the hydrogen maser, a device that provided a frequency standard of even greater stability over shorter timescales, further cementing his role as the principal architect of modern precision timekeeping. The legacy of Ramsey's work, however, extends far beyond the pendulum of a global clock. His method has evolved and generalized, becoming a foundational tool across vast swaths of contemporary physics. The basic principle of Ramsey interferometry, a sequence of poles, free evolution, and a second pulse to read out accumulated phase, is the workhorse of nearly all experimental quantum science. Modern atomic clocks, such as atomic fountain clocks and optical lattice clocks, are sophisticated descendants of his original beam apparatus. In these devices, atoms are cooled by lasers to microkelvin temperatures and tossed upwards against gravity, allowing for interrogation times of a full second or more, pushing precision to astonishing levels, capable of detecting the gravitational redshift predicted by general relativity over a height difference of mere centimeters. In the burgeoning field of quantum computing, Ramsey interferometry is the standard method for manipulating and measuring the state of a qubit. The first pulse, a pi over 2 pulse, creates the superposition. The free evolution allows the qubit to perform a computation or sense its environment, and the second pi over 2 pulse converts the acquired quantum phase into a measurable population difference. It is the fundamental grammar of speaking to and listening to a quantum processor. Furthermore, this technique underpins some of the most sensitive searches for new physics, from experiments seeking a finite electric dipole moment of the electron, a discovery that would signal new physics beyond the standard model, to searches for minute temporal variations in the fundamental constants of nature. The reception of Ramsey's method within the physics community was one of immediate recognition for its elegance and utility. The challenges were of an engineering nature, perfecting phase-coherent oscillators and improving atomic beam detection, rather than conceptual critiques of the method itself. It was so clearly a superior approach that it was rapidly adopted. Yet, there is a certain historical irony worth savouring. A technique conceived in the age of vacuum tubes to solve a problem in nuclear magnetic resonance has become the cornerstone of a 21st century quantum information revolution that its inventor could scarcely have envisioned. Ramsey's work was an early, and perhaps unintentional, foray into what we now call quantum engineering. He was actively manipulating the phase of a quantum wave function to extract information with maximal efficiency. This represented a philosophical shift from merely observing the strange consequences of quantum theory to actively harnessing its most delicate features for a technological purpose. The 4-decade gap between the publication of his method and the awarding of the Nobel Prize speaks volumes about the nature of foundational discoveries. Their full impact is often revealed over generations, as new fields of inquiry build upon the bedrock they provide. The prize, shared with Wolfgang Paul and Hans Dehmelt for their development of ion trapping techniques which offered an alternative route to long interrogation times, rightly honoured the pioneers who taught us how to hold an atom still and speak to it with time on our side. In conclusion, Norman Ramsey's separated oscillatory fields method stands as a monument to the power of conceptual clarity in science. Faced with a seemingly intractable physical limit, he did something more profound than build a better instrument. He reimagined the measurement process itself, by substituting a single, imperfect interaction with a carefully choreographed quantum dance of 2 pulses and a long phase accumulating intermission. He unlocked a new realm of precision. This singular insight redefined our very measure of time, gave birth to technologies that guide our world, and provided the essential toolkit for the ongoing quantum revolution. The Ramsey fringe is more than a feature on a spectrometer. It is an emblem of human ingenuity, a testament to the idea that the deepest secrets of the universe are often accessible, waiting for a mind that knows how to ask the question in a new way. His work remains a quiet, persistent, and foundational hum beneath much of modern physics, a legacy measured in the steady, unwavering take of the atomic age he helped create.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.